the inductive bias. An inductive bias is a model set of assumptions about the world which it uses here to generalize from limited training data. An LLM that has truly learned here Newtonian physics, the real law of nature, will have an inductive bias toward those functions that obey here gravitational inverse square law. Inductive bias towards the real laws of nature. The central thesis of the new research paper by Harvard and MIT is a foundation model has learned a real-world model if, and only if, its inductive bias aligns with the rules of that world model. Simple, elegant, but extreme power. So here we have it. We have now an inductive bias probe that we have. No? As an input, we have a world model and a foundational model, no? A transformer model, no? Lorentz function from the data. And now step one is fit the foundation model to syntactic data sets. I'll show you this in a minute. And we extract here the Lorentz function. I'll show you this in 2 minutes. And then step two is we just compared the Lorentz function to the given world model. And then we see if it's true. It couldn't be more elegant, no? Now, you have different approaches, but whatever you try to understand here in the internal mechanism of a language model, this is challenging. And therefore MIT and Harvard said, you know what? We have a different approach, a much more simpler approach. We just look at the result. So, the idea here of this inductive bias here offers here a beautiful connection between the foundation model or large language model and their inherent world models. Because physicists may train here a foundation model on a sequence of planetary orbits position. No? And since planetary orbits here obey the Newton mechanics, they might hope, and we all hope, also as an AI scientist, we hope, that the model, the language model, has an inductive bias toward those mathematical functions that really describe here the laws of nature, at least here in the classical limit here, the Newtonian mechanics. So we predict here the force vector between two planets, so here the Sun and the Planet. The authors from Harvard and MIT developed now an inductive bias probe for testing whether the foundation model's inductive bias really matches here the postulated world model's state structure. So the inductive bias probe repeatedly applies here a foundation model to a syntactic data set, I'll show you this in 3 seconds, consistent with the world model, and studies the extrapolated functions together. Here's the result of Mercury. Mercury, a little bit more of an elliptic orbital shape, at the predicted force. And you see where we are heading. Now, a world model, again, the definition. You start with a domain where the underlying rules are known. This is our postulated world model. Now, in physics, it's easy. We are defined by the masses, the position in the orbit, the velocity here of the planets here in the orbit. And the rules are simply in the classical limit, the Newtonian laws. We don't have to go with anything close to field theory or whatever. And we repeatedly create tiny new training data set now for the fine-tuning of the LLM. No? And each data set, of course, is consistent here with the world model, with the real laws of nature. And we fine-tune now, we fine-tune now here a pre-trained foundation model on each of these small syntactic data sets. And we then observe the function that this fine-tuned model has learned by seeing how it predicts on the training data set, how the output data set. Of course, it's the classical way. The key question is now, do the function that the large language model chooses to learn internally respect the structure of the true world model? Is it really here the law of nature? So they introduced 2 primary metrics here for the task with classical discrete states now, and they have an inductive bias towards the respecting state. It's very easy. Just imagine you have 2 different input sequences that lead to the same true state, so given the same output. Now, a high score of this particular metric means that the model doesn't create artificial distinction. It is really saying, oh, same output, great. And we have an inductive bias towards distinguishing the states. So if you have 2 input sequences that lead to different true states, to different outputs, A high score here means that the model successfully tells, hey, those are different states. Couldn't be easy, yeah? And the language model has learned now, this fine-tuned model here, an inherent world model, laws of physics, should score high on both metrics, both benchmarks. Now here we have it, July 9th, 2025. For me it is today, from Harvard University and MIT, and they did it. They did this big experiment. I wanted to find out, do we have ASI, AGI? Is really the emergence of intelligence happening? And we don't want to have a mechanical understanding. Is there intelligence created within an AI? But we just do here a simple probing. Such an elegant solution. So what was the setup? A transformer trained to predict the next position of the planet. This is Kepler. In many different solar systems with many different masses here. We can go from Mercury out to, Pluto is not a planet anymore. I still think Pluto is a planet. So yeah, so it becomes extreme accurate at this. No? This is the perfect Kepler system. And this model is then fine-tuned on a new task. Remember, here we just have the orbital information. So here Kepler just sees, okay, I have here on 364 days of the year, I know exactly where the planet is. And then on the 365th day, so the next token, the next time step, I can predict here the orbit, the X, Y, Z coordinates. This is Kepler. But now we say, we fine-tune now you on a new task. Given that we have the position on your elliptical trajectory, you should now predict, as a fine-tuned LLM, the gravitational force. So do you understand? This is the core element now of the real-world model. This is the core of Newtonian world models. You just predict the gravitational force that acts in the simplest classical limit with masses and distance. And here you have it. They did the big experiment. This is the Earth. And this is the Earth predicted here by the transformer model. After the pre-train, after the fine-tune on real data. And they even did this not only for Earth, for all the other planets. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Beautiful. And you see it's perfect case everywhere. Fine-tuned transformer when it had to predict the force, being perfect in being a Kepler to predict the next token prediction, to predict the next location of the planet in its orbit, to 99 point I don't know what accuracy, it failed completely to predict the force. So, but which model did it learn? The true Newtonian classical limit here? No. They did something clever, Harvard and MIT. And they could understand what formula, what function the LLM internally used for this prediction here of the gravitational force towards the sun. This is important. So the result is the model completely fails. Absolutely. It is not just inaccurate. The form of its error is what's revealing. Yeah? And the authors used here beautifully symbolic regression as a methodology to discover the inherent laws, the physical laws that the LLM actually learned, not the real correct laws of nature. But the LLM built something here within its neural network. And it was some absolute nonsensical physical formula. And they could look into this, and with symbolic regression, they could extract the mathematical formula. So what physical law the model actually learned? And it was this. So it was a complete failure. And you know what? It is even worse. It is even worse because the language model recovers here a different nonsensical law for every different solar system with different masses of the sun or of the planet. Whatever you put in, it's always creating a new law. It's never understanding that all the planets are governed by one law. The AI is not able to solve this. Absolute failure. But the model did not realizable world model. It learned here a variety, a collection of